In this video, we're going to continue talking about vectors and learn a way to multiply our vectors called the dot product. So let's get our definition of this dot product. If vector v equals a1, b1, and vector w equals a2, b2, the dot product v dot w is defined as v dot w equals a1, a2 plus b1, b2. And it should be noted that this result, when you do the dot product of two vectors, is a scalar. You get a number as the result. So let's do an example where we calculate various dot products. If vector v is -2, 6, and vector w is -3, -1, let's first find v dot w. So by definition, v dot w will be the first component of vector v times the first component of vector w plus the second component of vector v times the second component of vector w. And so I get 6 and -6, which is 0. For part B, let's find w dot v. So now my components for vector w go first. First component for vector w times the first component for vector v plus the first component for vector w times, second component of vector w times the second component of vector v. And we're going to get 6 minus 6 equals 0 again. So we got v dot w equals w dot v. Part C, let's try v dot v. So that's going to be the first component of vector v times the first component of vector v. So -2 times -2 plus the second component of vector v times the second component of vector v, 6 times 6. So this gives me +4 plus 36, which is 40. And last, let's just remind ourselves how to find the magnitude of vector v. Remember, that is the square root of my a squared plus my b squared. So I get the square root of 4 plus 36, which is the square root of 40, which I can simplify, but I just want to emphasize I got a square root of 40 here, and I got 40 for v dot v, and that's not a coincidence. So some properties of the dot product, some of which we just noticed in our first example, are as follows. So first, v dot w is equal to w dot v. Second, c times v dot w is equal to c times v dot w, which is equal to v dot cw. So it doesn't matter where the scalar is multiplied, you get the same result for all of those. 3, v dot w plus u is equal to v dot w plus v dot u. so it sort of has a distributive property. 4. V dot V is equal to our magnitude of V squared. That's what we noticed in that last example where we had 40 for V dot V and square root of 40 for the magnitude. And last, the 0 vector dot a vector is equal to 0. Notice it's not equal to the 0 vector because the dot product gives us a scalar as a result. So something else that we can use this dot product for is finding a way to express the angle between two vectors. So if theta is the angle between two non-zero vectors, V and W, then we have this relationship. Cosine of theta is equal to the dot product of V and W divided by the magnitude of V times the magnitude of W. So let's do an example where we use this relationship to determine the angle between two vectors. So find the angle between vector V, which is 5, -1, and vector W, which is -5, 12. And we're going to round to the nearest tenth of a degree. Well, if I'm going to use that formula that we just found, that cosine of theta is V dot W over the product of the magnitudes, well, I'm going to need to find V dot W, and I'm going to need to find the magnitudes. So let's start with the dot product. V dot W is equal to the product of the first components plus the product of the second components. So I get a -25 minus 12, which is -37. So I have V dot W is -37. Now I also need to find my magnitude of V and my magnitude of W, and then I'll be able to find the angle in between. So my magnitude of V is the square root of my A squared plus my B squared, which gives me the square root of 26. And the magnitude of W is the square root of that A squared plus its B squared, which is the square root of 169, which is 13. So now I can find the angle theta in between these two vectors by using that new relationship. My cosine of theta is equal to V dot W. So I would get -37, that's what I got for V dot W, over my magnitude of V times my magnitude of W. And that means theta is cosine inverse of all of that mess. Which rounded to the nearest tenth of a degree is 123.9 degrees. And that's the angle between the two vectors. So, if the dot product of our two vectors is equal to 0, then the angle between them equals 90 degrees. And we say the vectors are orthogonal. So if v dot w equals 0, then theta is 90 degrees. And we say that v and w are orthogonal. So let's do an example determining if two vectors are orthogonal. So are the vectors orthogonal? And we have S equals negative 2i plus j, and T is 11i plus 22j. Well, to figure out if they're orthogonal or not, I can just find the dot product. If the dot product is 0, then they're orthogonal. So the dot product of S and T, I would take my first component, which is negative 2, times the first component of T, so negative 2 times 11, plus the product of the second components, 1 and 22. So I get negative 22 plus positive 22, which is 0. So are they orthogonal? Yes, they are. So you can think of orthogonal vectors as vectors that intersect at a 90-degree angle, sort of like perpendicular, but we just use a different word when we're talking about vectors rather than lines intersecting. If two vectors are parallel, then v dot w is equal to the magnitude of v times magnitude of w, or v dot w is equal to the opposite of the magnitude of v times the magnitude of w. You get the first case if they're going in the same direction, which means that theta would be 0 degrees. And you get a negative in front if they're going in the opposite directions, which is when theta is 180 degrees. Now, sometimes we're going to want to rewrite a vector to be a combination of vectors that are parallel and orthogonal to another vector. So we need to learn how to decompose our vector in that way. So if v and w are two non-zero vectors, then first, the vector projection of v onto w is, they have weird notation for this, projection onto w of v equals the dot product of v and w over the magnitude of w squared times vector w. And two, to decompose v into vectors v1 and v2, which are parallel and orthogonal to W, respectively, we have V1, the one that's going to be parallel, is equal to the projection of V onto W, and V2 is V minus V1. So you would use this projection to find the one that's parallel to W, and then to find the one that's orthogonal to W, you just subtract the parallel one from your original vector. So let's do an example where we find this decomposition. For V equals 7, negative 3, and W equals negative 2, negative 6, we are going to first find the projection of V onto W. Well, let's just do that first. Our formula for that is the projection of V onto W is the dot product of V and W over the magnitude of W squared times vector W. So we need to figure out this magnitude and that dot product. Let's do the dot product first. The dot product V dot W would be 7 times negative 2 plus negative 3 times negative 6. So that is negative 14 plus 18, which is 4. Now I'll find my magnitude of W. My magnitude of W is equal to the square root of my first component of W squared plus my second component of W squared, which is equal to the square root of 40. So this means that my magnitude squared is just going to be 40. So this means that our projection of vector V onto W is equal to my dot product of 4 over my magnitude squared, so that's 40, times my W. And W was the vector negative 2, negative 6. Four over 40 is the same thing as 1 over 10. And then if I multiply component-wise, I get negative 2 over 10, which is negative 1/5, and negative 6 over 10, which is negative 3/5. So that is my projection of V onto W. Now for part B, we're going to find vectors V1 and V2. Such that V1 is parallel to W, V2 is orthogonal to W, and V equals V1 plus V2. So we're decomposing vector V into the sum of two vectors, one of which is parallel to W and the other is orthogonal. And we already said that the way to find these, V1 is just going to be your projection of V onto W. So I already have my V1 is negative 1/5, negative 3/5. We did that in part A. And then my V2 is supposed to be defined as v minus v1. So I can find v2 by just subtracting my v1 from the original vector. My original vector was 7, negative 3. And then I'm going to subtract my negative 1/5 and negative 3/5 to get v2 is 36/5 and negative 12/5. So this guy v2 is orthogonal to my original vector w, and v1 is parallel to w, and v1 plus v2 gives me my original vector v. Now, definition for us. If vector D is the displacement vector of an object, in moving the object in a straight line from point A to B under a constant force F, then the work W done is computed by W equals the dot product of force and displacement, and 2, W equals the magnitude of force times the magnitude of displacement times cosine of theta, where theta is the angle between F and D. We're going to do 2 examples calculating the work done in different situations, and then that's going to be it for our dot product video. So example. Find the work done by a force F equals 2I plus 7J in newtons in moving an object in a straight line from point A, negative 1,5, to point B, 911 in meters. So I know that work is going to be the dot product of my force vector and my displacement vector. And I have my force vector right here. To find the displacement, I just need to find the distance between my A and my B and write that as a vector. So my displacement vector I'm going to have my horizontal change times I plus my vertical change times j. My horizontal change is the difference between 9 and -1, and my vertical change is the difference between 11 and 5. So my displacement vector D is 10I plus 6j. So then I can find my work by doing the dot product of this displacement and my force. So work is equal to the force vector dot the displacement vector. And so I'm going to have work is my force, which was a 2I plus 7j, so that's 2, 7, dot my displacement, 10, 6. So work is equal to 2 times 10 plus 7 times 6, which is 20 plus 42, 62 newtons times meters. And that's all there is to finding the work when you have the force vector, and you can find the displacement vector pretty easily. Let's do one last example where we use the other formula for work that involves the angle in between. So a dog pulls a sled 200 feet across a yard on a horizontal path. She exerts a force, a constant force, of 25 pounds directed upward 15 degrees from the horizontal. Find the work done to the nearest foot-pound. So let me draw a picture just describing this angle for us. So the sled is being pulled horizontally, and we have a 15-degree angle, and that is our force vector going up at that angle. So I know my work is equal to the magnitude of force times the magnitude of displacement times cosine of theta. And do I have enough info to fill in all of this? Well, my magnitude of the force is that 25 pounds. So work is 25 times the magnitude of displacement is the 200 feet that the sled is being pulled. And my cosine of theta is cosine of 15 degrees. Now 15 degrees is not on our unit circle, so we'll have to type that into our calculators and then round it to the nearest foot-pound. So I get 25 times 200, which is 5,000 times cosine of 15 degrees. You type that all in and get that it's approximately 4,830 foot-pounds, rounded to the nearest whole unit. And that's all I have for you today on the dot product. So now you know how we can calculate different things using the dot product and find the angle between our vectors, figure out if the vectors are orthogonal or parallel, and answer problems about force. If you have any questions, feel free to drop them below, or if you're a current student, you can also ask in person, in class, in office hours, or through email. And I'll see you guys next time.